Okay, welcome to 3.1. We're going to be working with exponential functions now. So let's take a look. 3.1, exponential functions. Okay. So they kind of look like the reverse of a polynomial term. So instead of having like x cubed, you're going to have 3 to the x. Right? So this thing is the exponential function that we'll be interested in, not this thing. Okay, so this is a different object. This is associated with polynomials. This will be exponential. Okay, so let's take a look. Exponential function base b. And here it is. So f of x equals some number b raised to an x. We have restrictions on b. We want b to be greater than 0. And we also want b to not equal 1. Okay, if b is equal to 1, then this will just be a horizontal line. And there's issues if b is less than 0 with some of these exponents. For example, if b was negative, you might end up having to take a root of a negative, which wouldn't be real. Right? So we're going to try to avoid those guys. Right, so one thing to note on your calculator, the book is going to have you just evaluate, put this into the calculator and figure out what it is. You'll probably want to use your parentheses symbols. So, you'll see these things, these buttons on your calculator. You'll also have to use exponent symbols. So they look like that. If you've ever done My Math Lab or Math Excel, usually if you type that button, it'll give you an exponent as well. Some calculators also have this y to the x button, and you can use that as well. So, you may have a different calculator, but at the end of the day, it's kind of one of those things. Just look in the manual, and you'll figure it out. You can probably Google the manual online. I know a lot of people get their calculators on eBay and they don't come up with a manual. Anyways, let's look at 3 to the radical 5. I should have brought my calculator today. And see what we get. So to type this into my calculator, I'm going to go 3, hit the 3 button, and then I'm going to hit the caret button, the exponent button, then I'm going to hit the root button, and then I'm going to hit probably, my root button automatically puts a parentheses in there, but if it doesn't, you're going to have to put a parentheses in there, and then hit the 5 button, and then hit the parentheses button again, and then press enter or whatever your button is for evaluating. Okay, if you do it correctly, you should get 11.66. And let me go grab my calculator just to make sure. Yeah. Okay, so good stuff. All right. Once you are able to evaluate these things, you can, do some graphing. Obviously, you should be able to do some of these in your head, not like this guy, but like 3 squared or something. You should be able to do that in your head. But anyways, let's go ahead and take a look at graphing. We'll be doing translations here in a second, but you can also do a table to check your work. And obviously, if you're doing a translation like we did on the test, I would want you to first draw the basic graph and then do the translation. So to draw the basic graph, you can always use a table. Okay, so do table. Let's look at 16. And here we have our function g of x equals, the base is 1/3. And then it's raised to the power of x. Okay? So do a little table, x's and y's here. Let's go from -3 to 3 for the x values. Okay, and then we're plugging those in. We could do these in our head. We don't need the calculator. Okay, so we're going to plug these into here. And we have 1/3 to the -3. using our rules for negative exponents, if you have something like a all over b raised to the negative x power, you can flip the insides here and rewrite it as b all over a raised to the positive x. Okay, so that's exactly what we're going to do. Instead of 1/3 to the negative third, I'm going to write 3 over 1, which is 3, to the positive 3. Okay? And then 3 cubed, 3 times 3 is 9, times 3 is 27. Here we have 1/3 to the negative 2. And likewise, 1 over 3, flip it, it's 3 over 1, literally, if you need to see that, 3 over 1 like that. And then 3 over 1 squared, well, that's just 9 over 1, which is just 9. Okay. Sorry if these are too small to see. I'm sort of smushing this in, I know. 1/3 to the negative 1 is 3. And then anything to the 0 power except 0 is going to be 1. Let's sort of cheat here a little bit and get a little more room so we can see this. So 1/3 to the 0 power is 1. 1/3 to the first power is just 1/3. And then 1/3 to the second power is just 1/3 times 1/3 is 1/9. And finally, 1/3 to the third power is 1/3 times 1/3 times 1/3 is 1/27. Okay, so we want to take all these points and then plot them. Okay, so I'm going to come over here to my XY plane. Need a lot of room on the y-axis, right? So going 1, 2, 3. 1, 2, 3. Okay, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27. And then go and plot these guys. Sure, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Let's make my life a little easier there. Right, so what am I doing? Negative 3, 27. Negative 3, and then we're way up here at 27. Negative 2, we're way up here at 9. Negative 1, 3, 0, 1, 1, 1/3, 1, 1/9, and then 3 1/27. Okay, connect the dots. And what you end up with is what they call the exponential decay curve. Okay. So if you've heard of the phrase, it grows exponentially, this is the opposite of that. It's basically shrinking exponentially. Okay, so there's general characteristics of these graphs. Like I said, there's going to be an exponential growth, and it's kind of dependent on your base. Okay, so if your base is a fraction, you're going to have decay like this. It's going to go down. If you have a constant integer value, so or rather a natural number value here, like 5, 6, 7, it's going to be exponential growth. Okay? Okay, so let's look at that. The characteristics, the general characteristics of our exponential functions. Okay. First off, the domain. And for us, this is easy. All the objects we've been dealing with for the most part are the polynomials. I mean, in general, that's what I think of. The domain here turns out to be all real numbers, just like the polynomial functions. Okay. The range, though, a little bit different. It's going to go from 0 to infinity, not including 0. So nothing you can put into an exponential function will output a 0. Thirdly, the X-Intercept, there isn't one. And again, it's because there's nothing you could put into, For example, if you had a function y equals 3 to the x, there's no number you can put in for x that's going to give you y equals 0. Okay? It just won't work. On the other hand, there is going to be a y-intercept. So the y-intercept, you let x equal 0. If you put 0 in here, you have 3 to the 0. So you'll always get, putting in 0, you get 1 out. Okay. What else? The shapes. So again, there's an exponential decay and an exponential growth, and it's dependent on the b value. Okay? So if your b value is greater than 1, you get exponential growth. If your b value is in between 0 and 1, then you get the exponential decay. And that's what we saw in the last example where we graphed. Another thing then, 6, these things are one-to-one. So what do I mean by that? I passed the horizontal line test, and therefore they are invertible. Okay, so they're one-to-one, and hence they have inverses. Well, we're not talking about what they are yet, but we will see them, and we have to study those in great detail. Those are going to be the logarithmic functions. Anything else? There is an asymptote, a horizontal asymptote. So there's no vertical asymptote. This will just keep on going over and over and over. But there is a horizontal asymptote. And it's going to occur when y, the horizontal line y equals 0. So it's right here. It's on the x-axis, so you can't see it. When we get the shifting and stuff, the asymptote will shift with the graph. So as you lift it out of the original position, you'll see that asymptote sort of get carried along for the ride. Okay, so the Spdm transformations, we want to look at these, graphing these using transformations. And we can go through and talk about, what occurs when we do certain things. So for example, if you have y equals b to the x plus or minus c, that's going to be a shift either up or down. Okay, so this is your vertical shifts. And if you forgot and you have plus c, it's going to shift it up. Minus c, it will shift it down. Then you have your your horizontal stretch and shrinks. So what will that look like? You'll be putting a plus or minus c into the exponent like that. Okay. And of course, if you have plus c, it'll go to the left. If you have minus c, it'll go to the right. Then there's rotations. Of course, these have to go in a particular order. It's Hauser-V, right? So it's horizontal, stretch, shrink, reflection, and then vertical. Okay? I'm sort of doing them out of order, but hopefully you get the picture. So anyways, if you have y equals b to the negative x, then that's going to be a reflection about, I'm having trouble remembering, I believe it's the y-axis, okay? So y-axis, reflect. And then if you go y equals negative b of x, that's going to be your x-axis, reflect. What else? You have the stretches and shrinks. So if you have y equals b to the cx, this will be a horizontal shrink or stretch. And that's based off of the c value. Okay. Basically, if c is between 0 and 1, then it's going to be stretch. And then if c is actually greater than 1, that's going to be your shrink. And if you remember, if you've taken trig before, that's just what are you doing? You're messing with the period. Okay. Okay, so y equals then c times b to the x. This will mess with the amplitude. So it's a stretch in the vertical direction, stretch shrink. Vertical. And it has the reverse effects, right? So if c is in between 0 and 1, it's a shrink. But if c is greater than 1, then it's a stretch. So then we have horizontal, reflections, stretch shrinks, and vertical shifts. Okay, so that's that. Probably, for a test, I'll only worry too much about the reflections, the horizontal and the vertical. For these, they become, we can still do them, but I'm not going to worry about them for the test. So it's just these three I'm focusing on. And let's take a look at maybe some of the ones in the book. We got some checkpoints here. Those are always fun. So checkpoint 4, we have f of x equals 3 to the x. And then we want to plot g of x equals 3 to the x minus 1. They're also going to want us to give them the domain and range, okay, and that sort of thing. And they want you to draw the asymptote. In this case, you're not going to be able to see the asymptote, but okay, so what I'm going to do again is draw sort of my fundamental picture, this graph right here, this 3 to the x. So I'll go from -2 to 2. So I have 3 to the -2, which is the same as 1 all over 3 to the 2. So remember your exponent rules. If you have a to the -x, that's the same as writing 1 all over a to the positive x. So, 3 to the -2 is 1 over 3 to the positive 2, and then that's 1/9. 3 to the -1 is 1 all over 3 to the 1, which is just 1/3. 3 to the 0, of course, is 1. 3 to the 1 then is 3, and then 3 squared is 9. Okay, so we got a nice table, and we can go ahead and get our picture started. So 1, 2, and then let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2. Okay. So I got -2 and then 1/9. -2, 1/3. 0, 1, 1, 3, 2, 9. Okay, so that's sort of our fundamental picture. And then we want to use translations to get to our new graph. Okay, so I'm not doing a separate table now. I'm just using the translations on these points. So if you do a -1, what are you doing? You're shifting everything to the right. So we're going to take this point and shift it over here. It'd be nice if I had a different color, but I'll try. Take this point, shift it over here. Take this point, shift it over here. Take this point, shift it over here. Looks like we need another point. Take this point and shift it over here, and then connect the dots, and that'll be your graph. So it'll look like this. The domain and range are exactly the same for both of these functions. They'll never hit 0. This one's just all the points are over 1. So the domain of g is equal to the domain of f, which is equal to -infinity to infinity. The range of g is equal to the range of f, which of course is just 0 to infinity. It's not very interesting in that regards. Let's look at checkpoint 5. So this time we'll have a vertical shift. F of x equals 2 to the x, and then we want to also graph g of x equals 2 to the x plus 1. Whoops. And then this is going to be one of our vertical shifts. Okay, so again, I'm going to do a little table for the f of x. So I have an x and a y. You do the same values, -2, -1, 0, 1, 2. plug those values into our expression. So 2 to the negative 2, and then use exponent rules is the same as 1 over 2 to the 2. In other words, 1/4. 2 to the negative 1 is the same as 1 over 2. Yeah. And then 2 to the 0 is the same as 1. And then 2 to the 1 is the same as 2. 2 to the 2 is the same as 4. Okay, so we'll graph that guy. Ugh. Not much different than the above graph. So negative 2, 1/4, negative 1, 1/2, 0, 1, 1, 2, and 2, 4. Okay, so connect the dots, and then use translations on those dots to get your new graph. So 2 to the x plus 1 is essentially shifting all the y values up by 1. So this guy is going to go up to here. This guy is going to go up to here. This guy will go up to here. This guy up to here. This guy up to here. So our new graph will look like this. Okay, and one thing that's different now will be the range. The domain is the same for both. The domain is equal to the domain of f is equal to the domain of g is negative infinity to infinity. But the shift up has changed the range of g. So the range of f is from 0 to infinity, and the shift up is changing the range of g to 1 to infinity. And not only that, now we have an additional complicating factor. It's the asymptote. So you can't see, like I was saying before, you really can't see the asymptote of the generic exponential function. It's right on the y-axis. Okay? But then when you move this object up, that asymptote comes along for the ride. It's almost as though it's part of the graph. You know? So math isn't just about the things you see, it's about the things you don't see. And you'll find that to be true in art and, you know, literature, you know, writing the things that are, when you write, it's sometimes you think about what you don't say is just as important as what you do say. So, and it's in art the same way. What you don't draw is just as important as what you do draw. It's the yin and yang, I suppose. All right. One base that will come up a lot in our applications, if you keep taking math, you're going to see this guy. It's the natural base E. Okay. So let's take a look. Section 5 in my notes, the natural base E. And what is E? It's kind of like the number pi, but not really. It's transcendental, that's what they call it. It's 2.718281827, etc. It keeps on going on and on forever. It's kind of, it's like pi, 3.14159, and it goes on forever, right? You go look on YouTube if you want to know more about it. They do a pretty good job of giving you kind of the big picture. I'll just leave it for them to explain it to you. One other way to define this is kind of a funny way, and it comes up. So one thing I do remember is it comes up in business applications, and like some reason I remember them saying like 5,000 years ago they found these tablets. I mean, they found tablets from 5,000 years ago, and even back then, they're doing financial records and stuff like that. And this number kind of naturally appears when you're doing financial tabulations. I don't know if the number E was there, but they were doing financial transactions that far back. So you can imagine there's a lot of history here. So anyways, another way of defining this number E is saying as n goes to infinity, this expression here, 1 plus 1 over n to the nth power is going to go to the number E. Okay, so if you go to your calculator and, for example, you plop in 1 plus 1 over 10,000 and then raise that to the 10,000 power. So I can do that right here on my calculatron. So home, let's see, parentheses 1 plus 1 over 10, 1, 2, 3, and my calculator just died. 3, and then raise it to the 10, 1, 2, 3, and when do we get? We get 2 point, okay, calculator died again, 2.71815. Okay, so this is 2.71815. So you can imagine if you put in bigger and bigger values, it would get closer and closer to this number. Okay? So it's kind of an interesting deal. This thing comes up, this object comes up then, and like I was saying, in financial sort of matters where you're compounding interest continuously. Okay. Anyways, let's look at checkpoint 6. And one thing you should note on your calculator, so note furthermore, on your calculator, you'll have a special button for this guy, calculator. So if you want to figure out e cubed, which is approximately 20.09, you should have some sort of button on there that looks like e to the x. Okay, you just type 3 and then hit that button. It should give you 20.09. Okay, anyhow, let's look at checkpoint 6. We have f of x equaling 1145 times e to the 0.0325x. Okay. This thing is modeling biology, so it's a biology application. F of x is the gray wolf population. And X is the years after 1978. Okay. In biology, you can use these guys to model population growth. The only problem is kind of unrealistic. So as you study more and more math, what they're going to do is kind of start embedding more and more information in here. They have like a logistic growth equation and other kinds of stuff to make it more realistic. But this is kind of the fundamental example of population growth, what they use to model population growth. Okay, so anyways, let's see what they want. What is the wolf population in 2017? Okay. So what do? I'm going to have to plop this number into this formula. So it seems like it's just an application of can you use your calculator? So let's figure out what the x value is that we need. This will be 2017 minus 1978. Okay, so 39 is the number we want to plug in. So f of 39 then is 1145 times e to the 0.0325, and then times 39. And put that in your calculator, and we get approximately 4,067 wolves. Okay, the next section then we get to more financial matters. We're talking about compounding interest. So you put money in a bank, and they'll have an interest rate, and your money collects interest as it sits there, and as it grows, you get more money per year. Okay, because you'll have money in your account plus the interest that's thrown in your share account, and then you got interest on the money in your account plus the interest from the previous time period. So, anyways, let's take a look. Compound interest. Our formula A equals your principal plus the principal times the interest rate, which we're going to rewrite as P times 1 plus R. So let me define the variables. A is your accumulated value. P is the principal amount. So that's the amount that you put in your checking or your bank account on day one, okay? And then R is going to be the rate. And when we use it in equations, we're going to use it as in decimal form, okay? Okay, and one other thing in this book, we're assuming it's not some weird nominal rate. It's a per year rate. Okay, so per year. Okay, let's play around with this and see what happens over time. So we'll have year over here, and then our accumulated amount over here. And what's going to happen is we'll get a formula, and that formula is going to basically have kind of this shape to it, okay? And the idea is eventually, if you keep doing more and more interest, things kind of tend to this, to having this characteristic, this natural base E characteristic. So anyways, let's take a look. So in year 0, accumulated amount, all you have is the principal in there. Okay? So after 1 year, you'll then have the principal plus the interest on the principal. So P plus PR, which again, we're going to rewrite as P times 1 plus R. Maybe I should use some lines to help us out. Year 2, you'll have the amount in your account, so P times 1 plus R, and then plus the interest on that. So you'll have P times 1 plus R times R. Okay? So the thing about this is we can simplify the heck out of it. You know, we can factor out the P plus 1R, P times 1 plus R factor. So that's here and it's here. You can factor that out. So we'll have P times 1 plus R, and then the leftover parts, well, what's left over? It's just 1 here plus the R. And what happens? Well, you have P times 1 plus R times 1 plus R. We can rewrite that as P times 1 plus R squared. And let's go for year 3. So now you'll have the amount that's already in your account, P times 1 plus R squared, and then plus the interest on that amount. So you'll have P times 1 plus R squared times R. And then you just pull the same trick again. You can factor out this thing and this thing, and you'll be left with P times 1 plus R squared times 1 plus R. And of course, if you multiply this times this, you add the exponents. 2 plus 1 is 3, so you have P times 1 plus R cubed. Okay? So the point is, after doing this over and over and over, you can have a general formula. So for year T, we can predict how much you'll have in your account, right? So it'd be the principal times 1 plus R to the tth power. Okay. Note, like, that looks kind of like this. They have kind of the same form, kind of, right? So, right, how do we then bridge the gap between this and this? So, you know, I'm saying that that natural number E has something to do with interest. This kind of looks like it. How do we get from here to there? Well, you need to know a little bit more about the financial matters and compounding interest. Okay, so supposing instead of going a yearly interest rate, you have maybe a monthly interest rate. So you compound the interest 12 times a year. So instead of years over here, instead of a years column, we'll have a month column. And the resulting formula, if we were to do sort of an exploration of that, supposing we have n compounding periods per year, the formula that will result will be A equals P times 1 plus R over N to the NT. If you're interested in that, you're going to have to take like a business math class to really get into it. We just sort of throw it in your lap. Here it is, magic. But yeah, now it looks even more like the formula that we want. And if we do, instead of n compounding periods, we do continuous compounding, you're going to get the formula that I sort of, we'll get this formula that has the natural exponential in it, the number e, okay, the natural base e. So if you, supposing then we have continuous compounding, in that case, we're going to get A equals, basically, it shows you in the book, but this thing is going to turn into the number E, and you'll have A equals E to the RT. So I am, oh, sorry, the principal times E to the RT. I am kind of waving my hands here a little bit, but hopefully you can appreciate the sort of connection. Okay, I think it's clear that this kind of looks like this. And then if we do something special, we can say, all right, this is going to this. Just like back here, if we took n to infinity, we got this guy. And it's the same idea here. The number of compounding periods n, let's say we're compounding instead of 12 times a year, we compound 360 times a year. Then we compound 1,000,000 times a year, 1,000,000,000 times a year. You're going to end up with this number e popping out. Okay. Okay, so we have formulas for continuous compounding and some sort of non-continuous compounding, but more quarterly and monthly compounding periods. Let's look at checkpoint 7 just to make sure we can put all this in terms of what the book wants. The principal you're putting in is 10 grand. The rate given is 0.08, so 8% interest. And we're going to let it sit for 5 years in the bank. So how much do we have left over if we pick a quarterly rate? How much will be in the bank after 5 years? So we'll go back to our formula for n compounding periods from before. So we'll have 10 grand times 1 plus r, which is 0.08, all over n. So if it's quarterly, n is 4. And then raised to the 4 times 5, so the 20th power. Okay. And plop that into your calculator, and you get about $14,859. Right. The next question then, what happens if you do continuous compounding? What's going to happen? And I think personally, I'm like, well, if they compounding it second by second, I should have $1 billion. It turns out not to be that big of a deal, though. It's probably like $100 difference. So if you plug this into the formula, you get 10,000 times e to the r, which is 0.08, times t, which is 5. If you do that, you're going to get $14,918.25. So it's not even $100 difference. It's like 40, 50, 60, almost like $60 difference. It's not a huge amount of money. So, if you don't be conned into thinking that continuous compounding is going to solve all your problems, it probably won't. Okay, so that's 3.1. Okay.